As we discussed in the previous video, an atom is made up of a central part known as the nucleus, which contains particles called protons and neutrons, and this nucleus is surrounded by smaller particles, known as electrons, that orbit around it in various energy levels or shells. One of the most important things to understand is that the number of protons within the nucleus of an atom is what determines which element the atom belongs to. This number is completely unique to each element. The simplest and smallest element in the periodic table is hydrogen, because each hydrogen atom contains just one proton in its nucleus and one electron orbiting it. The next smallest element is helium, whose atoms consist of 2 protons and 2 neutrons in the nucleus, with 2 electrons orbiting around the nucleus. Overall, there are approximately 100 different elements known to science, and these have been arranged in a specific way within a structure known as the periodic table, where each box represents a different element. These boxes are called nuclear symbols, and they provide information about each element, such as its atomic number, which is the number found in the lower left corner of the box. The atomic number is critical because it tells us exactly how many protons are present in the atoms of that element, and therefore uniquely identifies the element. For example, if we see an atom that contains 2 protons, then we can immediately say that it must be an atom of helium, because helium has an atomic number of 2. Similarly, if we look at carbon, we find that it has an atomic number of 6, meaning that every atom of carbon must contain 6 protons. So, if we come across an atom that has 3 protons in its nucleus, it cannot be carbon, and instead must be lithium, which is the element with an atomic number of 3. Another thing to note in these nuclear symbols is the use of 1 or 2-letter codes that represent the name of the element. For example, the letter C stands for carbon, and the letters L and I represent lithium. Some of these symbols are straightforward and match the English names of the elements, but others are based on Latin or older names, which can be a bit confusing. For instance, the symbol Na is used for sodium and Fe is used for iron. Fortunately, most versions of the periodic table include both the name and the symbol, so if you are unsure about what a particular symbol stands for, you can simply look it up on the table. Now that we understand that the number of protons defines the element, you might wonder about the number of neutrons. Interestingly, the number of neutrons can actually vary within atoms of the same element. This means that while all atoms of a particular element must have the same number of protons, they can have different numbers of neutrons. When this happens, we refer to these different versions of the same element as isotopes. The definition you need to remember is that isotopes are forms of the same element that contain the same number of protons but a different number of neutrons. To help make sense of this, let us take the example of carbon. The most common isotope of carbon is called carbon-12, and it contains 6 protons, 6 neutrons, and 6 electrons. However, there is another form known as carbon-13, which also contains 6 protons and 6 electrons, because it is still carbon, but it has 7 neutrons instead of 6. Because it contains a total of 13 particles in the nucleus, 6 protons plus 7 neutrons, it is called carbon-13. Since the only difference between isotopes is the number of neutrons, they generally behave in the same way chemically, because chemical reactions involve electrons and not neutrons. That is why all isotopes of an element usually participate in the same types of chemical reactions, even though their physical properties like mass may differ. Speaking of mass, when an element has more than one isotope, we often want to know the average mass of all the different isotopes that occur naturally. This average is called the relative atomic mass and is represented by the letters A and R. To calculate the relative atomic mass, you need to know 2 things for each isotope. First, you need to know the mass number of the isotope, and second, you need to know its abundance, which refers to how common or rare that isotope is in nature. For example, let us look at copper. Copper has 2 naturally occurring isotopes. One is copper-63, which has a relative abundance of 69.2%, and the other is copper-65, which has a relative abundance of 30.8%. When we talk about abundance, we mean what percentage of atoms in a typical sample of copper are of a particular isotope. So if you picked up a chunk of copper, about 69.2% of the atoms in it would be copper-63, and about 30.8% would be copper-65. In an exam question, you might be asked to calculate the relative atomic mass of copper to 1 decimal place. The formula for relative atomic mass is the sum of each isotope's abundance multiplied by its mass divided by the total sum of all abundances. So for copper, we take the abundance of copper 63, which is 69.2, and multiply it by its mass, which is 63. Then we take the abundance of copper 65, which is 30.8, and multiply it by 65. This gives us two results, which we then add together. So 69.2 multiplied by 63 equals 4,359.6, and 30.8 multiplied by 65 equals 2,002. Adding these gives us a total of 6,361.6. To finish the calculation, we divide this total by the sum of the abundances, which is 69.2 plus 30.8, giving us 100. This makes sense because the total percentage of all isotopes should equal 100%. So we divide 6,361.6 by 100 to get 63.616, which we round to one decimal place as 63.6. This final value is the relative atomic mass for copper, and it represents the average mass of a single copper atom, taking into account the mixture of isotopes found in nature. We denote this value with the symbol A and R, and it is used to compare the masses of atoms on a relative scale. Understanding how to calculate and interpret this value is essential in many areas of chemistry, especially when dealing with chemical equations and molar calculations.